Welcome back to Physics Fundamentals. In this video, I want to talk about net force. Our goal with net force is to be able to model what happens when more than one force is acting on an object at the same time. In order to make sense of this, I'm going to start off with a computer simulation. I apologize in advance, the screen is about to become very bright. But this simulation is brought to us by PhET, P-H-E-T. It is available for free online. There will be a link in the description so that you can find it and play around with it if you so desire. We've studied in the past the idea of force, Newton's law. An object at rest will stay at rest unless an outside force acts on it, like this guy pushing this refrigerator. If we apply force, we will cause the refrigerator to increase in speed. And it will continue to move at the exact same speed until some other force acts on it, causing it to slow down. And if I can get this just right, I will get this refrigerator to come to a complete stop. One of the other things we know about force is if we have a more massive object, it takes more force to get it to accelerate. If we have a less massive object, then applying the same amount of force is going to cause a much greater acceleration. I don't need to make this come to a stop, but if I do, it's going to make my computer a little bit happier, because this simulation will continue to run into the background as I come over here to look at net force. Well, what happens if I have just one force acting on this cart? It's going to move at increasing speed without too much effort at all. If I try to counteract that by applying some force in the opposite direction, well, we have a greater force on the blue side and a lesser force on the red side, so it still moves, but not quite as fast. If I keep stacking up forces, we can get that to continue to be the case. Or maybe I can I didn't get it fast enough. Let's see if I can get this to actually work. Let's let that cart go over that way for a little while, and then let's stack the deck and see if we can get that cart to slow down and eventually start moving in the other direction. And we can balance out the forces, but balancing out the forces just causes no acceleration. Once the cart is already moving, it continues moving. Mathematically modeling this turns out to be fairly straightforward. If we simply take all of the forces and add them together with positive and negative signs as appropriate, the resulting value gives us the net force. So the net force, I like using the Greek letter capital sigma, which you may have come across in a previous mathematics course, especially if you've ever studied anything involving statistics. That means add everything together. So sigma F is what we're going to use to represent the net force, and it is the sum of all of the forces that are acting on the system. Some of them are going to be positive, some of them are going to be negative. That's okay. All right, so if I put some numbers to that, let's say that I have an object whose mass is 200 kilograms. Let's make it less massive. Let's just make it 20 kilograms. And on the blue team, I have one person who is pulling with a force of 100 newtons. On the red team, I have two people who are each pulling with a force of 30 newtons. The blue team was pulling to the left, so that would be a negative force. The red team was pulling to the right, so that would be a positive force. I can calculate here that the net force is negative 100 newtons plus 30 newtons plus 30 newtons, which all told comes out as negative 40 newtons. And then, of course, I know Newton's second law, F equals ma, which I can rearrange and write that A is force over mass. Right? The fact that it is net force, it has two characters to represent its variable, but it's still just a variable and it can be manipulated like everything else. We can plug in and when we do this division, it looks like it's going to come out at negative 2. And of course, newtons divided by kilograms is meters per second squared. Another idea that we have come across, but I want to start putting some theory into place on, is the idea of a pulley. We know that a pulley will allow us to take a length of rope and change its direction. We can use that to attach, say, a cart on the air track to a hanging mass. But what I want you to think of with a pulley is a tool for changing direction. So the x-axis bends along with the pulley. And that's even the case in the extreme example of, let's put a pulley hanging from the ceiling with two masses attached to it. All right, so there is my x-axis, or maybe my y-axis, I don't know, but it bends around the pulley. So the net force here is the force acting on mass 1 plus the force acting on mass 2. It looks like the force in question is going to be gravity, right? We know that gravity is an acceleration. The acceleration due to gravity is m times g. We call that the gravitational force. We often put a subscript of a g on it. So the force acting on mass 1 is pulling in this direction. The force acting on mass 2 is pulling in that direction. And with our x-axis being bent the way it is, that's the positive direction and that's the negative direction, even though they are both downward directions. So the net force here is negative m1 times g and positive m2 times g. This type of a mechanism is called an Atwood's machine. And it's a nice way of being able to deal with balancing forces without having to try to find a way of setting up a larger mechanism. If you feel like this lesson was a lot of setup without a whole lot of payout, you're honestly quite right. thinking about things in terms of multiple forces acting on an object, thinking about things in terms of pulleys bending the axis, and which thing is positive and which things are negative, can be a little bit counterintuitive, can take a little bit of experience. So I just want you to think about systems. I want you to think about where the forces are, where positive forces are, where negative forces are. And if we can get that much down now, then we'll be able to do much better as we move on from here. So for now, thank you as always for joining me, and I'll see you in the next one.